So say that I'm standing around a campfire, or maybe I'm standing in front of a fire in a fireplace, and say that for some reason I'm holding this long piece of metal. This is just the, I think it's made of aluminum, but I'm not really sure. It's just the tray that goes down here at the bottom of the whiteboard. And say that I'm holding that, and I decide, for some reason, to put the end of it into the fire, into the fireplace or the campfire, and just hold on to it. Just with my bare hand here, just hold on to this piece of metal. How quickly is this piece of metal going to hold up? Going to heat up, if I can talk, going to heat up so much that I have to drop it. How quickly is that going to happen? It's going to happen pretty fast, probably within a few seconds, right? Well, compare that to if I had this wooden yardstick. Now, why I would be standing in front of a fire holding a wooden yardstick, I don't know, and I don't know why I would want to put it into the fire. Right? How long would it take for the heat to get from one side all the way to my hand? Well, it's going to take a long, long time. In fact, the end of this is going to catch on fire before I have to let this go, right? I can just hold this and the end's going to be on fire. It takes that long for the heat to get all the way down compared to this long piece of metal. And why is that? Well, in the TEKS, it talks about conductors and insulators, and we could be talking about sound, about conducting or insulating against sound. We could be talking about light energy. The TEKS talks about electricity and heat, right? Thermal energy. And we know that, we probably all know that metal is going to conduct, and something like wood is going to insulate, right? So what does that mean? We could just leave it really simply. We could leave it at an insulator is resistant to heat energy or electrical energy passing through it. It doesn't mean that it doesn't allow it. It just means that it's resistant to it going through. And there's different degrees of resistance, but we're not going to worry about that. And we know that a conductor, such as this piece of metal, it allows, it's not resistant to heat energy or electrical energy going through it. And we could just leave our understanding at that and just call it a day. That'd be a really short video. But that leaves a lot of questions unanswered. And the big question is why? What's going on within this piece of wood that keeps the electricity or the heat from moving through the piece of wood here? What's going on inside the piece of wood? And I'm talking about at the atomic level, within the molecules and the atoms and the electrons, right? Way down there, the atomic particles. What's going on there that keeps that heat or the electricity from going through it as compared to in the piece of metal? What's going on inside here that allows the heat or the electricity to go through it really quickly? What's going on there? And that's our question for this video. Now, we're going to start with this. What are we talking about? Well, we're talking about metals and non-metals. And I get my marker. Our periodic table, maybe you can read that. It's kind of small to read, but we're not going to worry about specific elements here. I mean, I'll talk about a couple as an example, but we don't need to get into nickel and copper and zinc and neon and a lot of specifics here. I just want you to see the proportions. So these are the non-metals. Hydrogen over here and here, like that. Hopefully you can see that in blue. It's just this area, the non-metals, just this part, and hydrogen over here. Everything else, they're metals or metalloids. We don't have to worry about a metalloid. That's this area in here. But we're just going to consider them metals, and that's, for our purposes, that's enough. So just a few are non-metals, and almost all the other elements are metals. And why does this matter? Well, because the answer to our question of what's going on inside the wood or inside the metal has to do with how the atoms in the element, how the molecules, how they bond together. So let me pause for a moment and write a definition up here. All right, let me get a marker, and we'll put this up here. So conductor, insulator, insulator resistant to heat or electricity, passing through it, not resistant to heat or electricity, passing through it. And our question is why? Now the question here is why? Why is an insulator resistant but a conductor is not resistant? All right, so question is put over there. Our question is why, and our answer is it's about the bonding. The type of bonding. What that means is how the atoms, how the molecules, how they fit together. So say that our two balls here, say that these were two molecules or two atoms. How do they join together to form a molecule? And the answer is that it depends on what's getting joined together. So and there are three kinds of bonds, and I'm going to write them down. But if a non-metal is joining with another non-metal, so hydrogen and oxygen, or nitrogen, or phosphorus are getting joined together, that's going to form one kind of bond. If a non-metal and a metal, that's another kind of bond, and a metal to a metal, that's still another kind of bond. And they're called different things. They have different names. So a non-metal, well, let's do the other one. Let's do the non-metal to a non-metal. Okay, that's called a covalent bond. So 3. That's probably too high. Let's erase that. I probably can't read that up there. So 3 types of bonds. One's called a covalent, non-metal to non-metal. Again, what does that mean? Non-metal to non-metal? It's over here. Anything on this side, the non-metal, chlorine and iodine and oxygen, nitrogen, carbon, and so forth, non-metal to non-metal, covalent bond. Ionic bond. Non-metal to metal, and a metallic bond. Metal to metal. Now, we're going to divide it up here. We're going to focus on metallic bonds. We're going to put covalent and ionic bonds together. You probably don't need to remember, I mean, if you want to study it. It's not going to hurt you to remember this because it's not all that complicated. It's just a matter of just remembering non-metal, covalent, right? But you probably won't be asked about the difference between the bonds. It is useful to know that these two are pretty similar. A covalent bond and an ionic bond are pretty similar in the way that the atoms fit together. We're not going to flesh out the details here. I'm going to use just one of them as an example and say, well, the other one is pretty similar, so let's just remember that, okay? And we're going to compare that to a metallic bond. Now, in order for us to do this, we have to take a quick review, because this stuff's pretty complicated, but I'm trying to show you in the simplest way that I know how, and that I think is just going to be useful for you to remember our answer to our question of why something acts as a conductor for heat and electricity and something acts as an insulator for heat and electricity. So to do that, we have to take a quick review of atomic structure. Okay? Quick review of that. So remember that in an atom here, we have, I'll do it about here, I guess, the nucleus, and almost all of them have protons and neutrons inside. Now, you might have seen pictures of old pictures of electrons kind of orbiting like this, right? You might have seen that. And then you have these little negatively charged, because protons are positively charged, neutrons have no charge, and electrons, I'll put a little E over there, seen them orbiting around the nucleus. That's an old picture. It comes from Niels Bohr from 100 and something years ago, a long time ago. That's not the way it works, right? With quantum theory, quantum mechanics, scientists have learned that electrons don't orbit in these kind of fixed patterns around a nucleus. Let me erase this. They don't orbit like that. They do move around, but it's hard to tell where they are, and it's kind of random, and actually kind of where they are depends on when we measure them, and that gets really weird in quantum mechanics, because we kind of decide where they go, but we don't have to worry about that for our purposes. What we do need to know is that they orbit in shells. So there's a shell. That marker's not going to work. An energy level: 1, 2, 3, 4, 5, 6, and 7. 7 different energy levels. And electrons, they move around somewhere in the different energy levels. Now, each of these energy levels has a different number of electrons, at most. So I'm going to put over here level L1 is at most is 2. And that goes to all the way down to level 7, and this is 1. There's 1, that's 7. Okay, so it goes out. You follow me? Right? So level 1 is the innermost here, and level 7 is the outermost. And at the innermost, 2 electrons. It has no more than 2 electrons somewhere inside this energy level here. Okay? To level 7 is 90, and I forgot the number, 98. 98 electrons. We'll have 98 electrons. Now, not all elements have that many electrons. Some only have a couple of electrons. We can take hydrogen. Hydrogen over here is 1 up there. That means there's 1, I don't know if you can see that, it's kind of small, but there's 1 proton in the nucleus of hydrogen. There's no neutrons actually in hydrogen. Hydrogen's kind of weird that way. And there's 1 electron. So it could have 2 in this innermost shell, but it just has 1. Right? So hydrogen's super common, of course. And there's just 1 proton, 1 electron. I use that as an example that not all of them have 2 or more, or 6 or 8 or 10 or however many. We can use another example. We can use oxygen as an example. And I'll take oxygen. All right. So oxygen has 8 electrons. It has 8 electrons. So if we take the nucleus here, it's kind of small, but I got to fill up this whole board. Now, there's 2 in there, and then on the outside there's 6 here. And it has 6 there, right? and that's an oxygen. So hydrogen has only one, oxygen has just a little bit more. Now the next thing that you need to know that helps us answer our question has to do with this part of the molecule, the atom of the molecule, and this energy level right here, this outer one, whatever the outer one is, and in oxygen there's two energy levels, right? There's one with 2 and one with 6. This is called the valence energy level. Valence, if I spelled that right, hopefully I did. Yeah. So these are going to be called valence electrons. All that means is it's in the outermost energy shell in a particular molecule, right? So in oxygen, these here in the 2 here in the first energy level, those are not the valence electrons. Here, the 6 and the outermost, those are the valence electrons because it's the outermost energy level. If I had something like aluminum is the metal, aluminum, put a box around oxygen, aluminum has, let me have 2, 8, and 3, that's right. It's got 3 energy levels. The first energy level, L1, has 2 electrons. And I could draw it like this, right? Draw it kind of small. And it's got 1, 2, 3 circles around it, okay? And L1 is the innermost, L2 second, level 3 here. And this is L2, that's L3. Second level has 8 electrons, third has 3 electrons. What's the valence? The valence shell or valence energy level is this last one with the last one with 3 electrons. Okay, why does that matter? We have to compare how these molecules are put together, and we'll do it over here. So let's say I have this oxygen. Okay, say I have the oxygen molecule. Well, I got oxygen here. No, I'm sorry, water molecule, not oxygen. Let's do a water molecule. All right. So I have oxygen. That's kind of like this. This is our oxygen. And I'm gonna put it, oh, well, it's gonna be hard to read. Oxygen, it's kind of small. Maybe you can read that, I don't know. Oxygen, and it has, here you got 2 here, and I got some more there. Now remember that oxygen has 2 electrons here in the first level. Maybe if I did that in blue, maybe that would be easier to see perhaps. Maybe purple will work. Let's see if purple works. Yeah, purple works. Let's do that. I got 2 there, right? Because where am I? Oxygen. Yeah, 2 on the innermost. And then there's 6 on the outer. So I want to put 2 here and 2 over here. Just kind of the way they form up. Don't worry about why. That's going to get kind of even more confusing. So don't worry about that. Just know that they kind of separate a little bit. And then I'm going to put 1 here and 1 there. So I have 8. 1, 2, oh, well, sorry, 6. 1, 2, 3, 4, 5, 6. But then I have my hydrogen. I got hydrogen here. Because it's H2O, so it's 2 atoms of hydrogen, 1 atom of oxygen, and water. This is our water molecule. Right? Well, hydrogen has its own electron. Right? Hydrogen has an electron. We'll put that in blue. And these kind of join together, right? Why is that? Because the outermost shell here of hydrogen can have 2 electrons. And it wants to pair up, okay? So what it makes is, just in short, it makes a really tightly bound molecule. That's what I'm getting at. right? Why it's the case, it's not even really going to matter why these electrons want to pair together. Just know that they do want to pair together. And it makes really tightly bound molecule, right? These electrons, it holds on to the electrons, okay? So non-metals want to hold on to their electrons. It's not the case for metals. Let's take our molecule of aluminum. I'm going to do it right under here. I think you can see that, of aluminum. Well, aluminum, it forms a lattice. A lattice is, well, it looks like this. So, like that kind of. I'll put A for aluminum, or AL for aluminum. AL for aluminum. That's the nucleus, okay? They're all for aluminum. And here we go. We have 2, 8, and 3. So there's a bunch of levels here, okay? Each one of these has its electron shells, all right? You notice that they're going to overlap. And they do. All right, let me keep drawing. 1, 2, 3. 1, 2, 3. Okay, now I'm not going to draw all of the electrons in here. The 2 on each of these, I'll just do it once, because then it's kind of ridiculous. It's going to get too much. I'll do it once. And it's probably kind of hard to see anyway, right? It's real small, okay? And then you have 8 here. 1, 2, 3, 4, 5, 6, 7. That's a lot of circles. And then we have 3 here, right, on the outside. So I have all of my aluminum atoms here, and they're all lined up in a lattice, so it means it's an order like this, and it could just go on and on and on, right? It'll be like so it's not going to be all mixed around, right? It's going to be like this. And what metals do that non-metals don't, and this is really the key point. Non-metals, they hold on to their electrons. They're tightly bound. So in this piece of wood with the phosphorus and carbon and nitrogen and oxygen and everything else that's in a piece of wood plus whatever else is in here, the electrons are tightly bound together with their molecules. And the molecules are, I mean, they're all stacked up against each other, of course, but they're not stacked in a lattice like this. They're just kind of, well, they're more random, right? In a metal, the electrons in the valence shell, the outermost shell, the valence shell here, in the aluminum or the copper or the iron or whatever it is, they share from one atom to another, and they're loosely held because metals want to get rid of electrons. Non-metals want to keep electrons. Metals want to get rid of electrons. And some of these valence electrons get broken off. We don't have to worry about how they get broken off when the molecule forms, but they do when they become free electrons. So I'm going to write that here. Free, this is, grab the wrong marker. This is an important term here. It's a crucial term. Free electrons. This over here. Free electrons. And these free electrons, they float in this, it's like a soup. It's like a sea. They call it a sea, an electron sea. They float around in here. In here, they can just kind of float around from atom to atom. If you can see me doing all that here, it's getting kind of dense. In this piece of metal, the electrons in the valence shells here, and between, well, not the valence electrons, but among, at that level, the free electrons are just moving around from atom to atom. These kind of float around, and that makes a really big difference. It's really important because the electrons here in the non-metal, they don't move around freely. In the metal, they move around freely. So what does that mean? It means that how does the heat move, right? How does heat move? Heat is just, energy is really just vibration. It's just a particle moving. if we wanted to really oversimplify, to come up with a helpful oversimplification, energy is just movement. It's some kind of movement. It's a movement of a photon or some kind of particle. In this case, we're talking about electrons, and it's movement. Say this is an electron, and it's moving. It could be oscillating, it could be shaking, rotating. There's different kinds of movement. It doesn't matter what the movement is. Energy is just movement. So it's still, there's no energy. Well, no kinetic energy anyway, right? That we're going to get to, kinetic and potential. But movement, right, with this kind of energy anyway, with heat energy and electrical energy, we're talking about movement of particles. Well, here in this wood, the electrons, they vibrate. And they vibrate, and they vibrate. And the atoms vibrate, and the molecules vibrate. But then it has to vibrate and bump up against the next one. It causes this one to vibrate. And then it has to bump up against the next one. And that causes this one to vibrate. And then so forth. And that's a really slow process. In a metal, you have these loose, and they're tightly bound, so they really don't want to move, right? These things don't want to move very much. Here in a metal, you have these free electrons that are floating, that can be vibrating, and they're bumping up against everything inside this piece of metal. And these electrons, they're bumping up against all the other pieces of aluminum, of the other free electrons, which are bumping up against the other electrons, and it goes quickly, really fast. If you haven't, if you were to hold a pot on a stove, you know how quickly that iron pot gets hot if you're just holding on to the cast iron pot or any kind of pot, aluminum pot. If you're not holding on to something that's an insulator on a handle, your hand's going to get really hot really fast. So you know how quickly that moves. That's because the electrons are moving really fast through the metal, vibrating. These free electrons, they're bumping up against all the other electrons in there, causing everything else to move faster. And that's the answer. That's why the heat moves really fast through, and electricity is really similar. Electricity it's similar. The movement is similar. The action of the free electrons is really similar. It has to do with a charge and a moving charge. And there's going to be a video later on about electricity. Just know that the similarity is that there's these free electrons that move around inside the metal that don't exist inside a non-metal, and that's why something like wood or another kind of insulator takes a long time for the heat to move through. It moves through, right? Heat will move through an insulator, and some materials insulate better than others, of course. It's not to say that an insulator doesn't allow energy to move through it at all. It's just resistant to it. A conductor, when we're talking about a metal, it allows it because of these free electrons just moving really quickly and bouncing against everything and moving it through. And that's the answer. There's something else though. There's one other part of this. Really, there's maybe two other parts of this. But what else do metals do? Metals can bend, right? So I can break it. But if you have a metal spoon, or we take copper and we roll it into wires, well, that's ductile. So metal can bend, it's malleable, right? I can move it around, right? And that's because of the structure here. And I can roll it into wires, right? So that's why we have copper wiring, for example. I could get it really thin and roll that copper into a wire. That has to do with the structure. Because if I move it, let me draw a little bit bigger. Well, I'll draw some more. Well, I'll do it like this. So this is, put it like about right there. That's not good. Keep getting the wrong marker. Where did my marker go? There it is. So let's draw them here. Aluminum, 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 aluminum. And this is positive, right? These are positive. Positive, okay? I'll start drawing P's for protons. So these are going to be positive. Positive, positive. Okay? This is that lattice I was talking about, right? This is the lattice. And then let's say I move it. Say I shift something. Say I move some of it up. okay, say I take these and I move it down, you're always going to have the same structure. It's always a lattice of positive protons, positively charged protons, surrounded by all these free electrons. So there's always an attraction because positive and negative attract to each other inside a cell like this. There's always an attraction. No matter how you move it around, there's always an attraction. Well, say I have this one. This is going to be really kind of tough to draw here, but hopefully I can make it work for you so you can see it. This is a nonmetal. A nonmetal to a nonmetal. Inside the molecule of a nonmetal. Well, I'm going to have positive, negative, negative, positive, positive, negative, negative, positive, and so forth, okay? Well, then what if I wanted to move this? I'm just going to do 2 levels. I really should show more, but hopefully this is going to work. Well, say I wanted to shift this row right here down, okay? Say I'm breaking this. I'm moving this piece of wood, okay? Well, I still have positive, negative, positive, negative. That's proton, electron, proton, electron, proton, electron, right? Proton, electron, so forth. Right? And I'm going to move this one down. Notice. Here, they were all positive, negative, positive, negative, positive, negative, right? You'll see that? It's kind of hard to see here. Positive, negative, positive, negative. Now I have negative, negative. Negative, positive, positive, negative, negative, those things are going to repel, right? So that's why nonmetals don't bend as a rule. As a rule, they don't bend. I mean, we can get into specifics and we can find some examples of that. But at the atomic structure, so the answer to our question has to do with the atomic structure of metals and nonmetals, how they bind together to form, how the atoms bind together to form molecules, and that this bonding, the covalent and ionic bonding that have to do with nonmetals, they don't form the right kind of bonds that allow energy to go through. They resist energy because, why? Because the electrons are tightly held. And it takes a long time for that energy to move from one to the other, right, our electrons here, to the other, to the other, to the other. Long time to get down the chain. But in, well, that was loud. But in a metal, such as the aluminum here, or whatever this is, there's all these free electrons. And they just zip through, bouncing off of everything else. I think this is really fascinating. I don't know if you do, but I do. Bouncing through, and that's why what's going on at the atomic level in the bonding explains why something is a conductor or an insulator.